Welcome to this explainer. Listen, most people look at industrial rice milling and think, oh, it's just a quaint agricultural step. You're just taking the shell off a grain of rice. Well, absolutely not. If you actually look at the data, it is a brutal, high-stakes battle against mechanical entropy and biochemical degradation. Precision is literally everything here. We are navigating a microscopic minefield where a single millimeter of mechanical misalignment or just a fraction of a percent in your moisture tolerances is the exact difference between a highly profitable premium product and a warehouse full of completely ruined, unsellable inventory.
Because the exact second you violently shear that outer protective husk off the raw paddy, you trigger a metabolic countdown. It's called enzymatic oxidation. The moment those cell walls fracture, endogenous lipo-oxygenase enzymes are released straight into the lipid fractions of the grain. And if you don't mitigate this immediately, it's game over. The enzymes basically go to work digesting the lipids, triggering severe lipo-oxygenase rancidity. What was once a nutrient-dense, shelf-stable product becomes rancid, unpalatable, and completely commercially compromised in a matter of hours.
So, we're going to rigidly audit this process across 6 operational areas. 1. The enzymatic threat. 2. The economic delta. 3. Dehulling mechanics. 4. The moisture critical window. 5. Friction mechanics. And finally, value stabilization.
Section 1. The enzymatic threat and navigating anatomical traps.
You really have to look at the sheer anatomical vulnerability of the paddy caryopsis. Pay close attention to the aleurone layer in the germ, the embryo, sitting right there at the edge of the endosperm. This is exactly where the vast majority of your lipids and enzymes live, trapped in incredibly close proximity, separated by nothing but delicate cellular structures. It's a literal anatomical trap. If your machinery applies just a tiny fraction of excessive shear or compression, those separate components mix. The second the physical integrity of that aleurone layer is mechanically breached, your product's commercial value starts dropping to zero.
Section 2. The economic delta. Or, as I like to call it, surviving the silica wall.
Let's coldly look at the blunt financial reality of your mass balance. Every metric ton of raw paddy comes with a built-in architectural defense mechanism. Look at the hull waste. It accounts for 20% of your total mass. But look at the composition profile. It's 94 to 96% ash. The high silica density is staggering. That means a full 1/5 of the raw material dumping into your facility is essentially a highly abrasive silica trap that is actively trying to chew up and destroy your expensive industrial machinery at every single turn.
Which brings us to your absolute ceiling, 70%. This number is your financial ultimatum. The absolute preservation of this 70% head rice yield is quite literally the only thing keeping your plant profitable. Head rice is your intact, unbroken kernels. The moment a single kernel snaps in half from mechanical stress, it drops into the brokens category, and you're selling it for pennies on the dollar. Your entire operation is a hypersensitive balancing act to rip off that 20% silica armor without compromising the 70% starchy endosperm. Every snapped kernel is margined down the drain.
Section 3. Dehulling mechanics, speed differentials, and friction spikes.
We have thankfully evolved past the brute force caveman mechanics of older tech like the crude Engelberg paddy huller. Now we rely on the precise opposing rotation vectors of modern rubber roller speed differential systems. The rough rise passes between 2 distinct rubber-coated rolls, turning in opposing directions, mismatched at very specific velocities. The gap, the compressive pressure, and the speed differential create a shearing action that ideally strips away the silica hull. But, and this is a massive but, that compressive pressure must be exactingly managed.
Which brings us to point of failure number 1, roller overpressure. If your floor operators get greedy and overpressurize these rollers to chase a slightly faster throughput, they aren't just slightly discoloring the rice, they are entirely annihilating plant uptime. The physics simply do not forgive. Excessive pressure crushes the delicate starchy endosperm, tanking your head rice yield. Concurrently, pressing rubber rolls that tightly against abrasive silica slashes your rubber roll life to below 100 hours. You're basically creating your own maintenance bottlenecks and destroying your own product.
And the mechanical catastrophe cascades from there if your gravity separators fail. Say you get subtle fluidization drifts. Step 1, unhusked paddy completely bypasses separation. Step 2, that rough silica paddy inadvertently drops into your downstream pearlers, which are only built for soft brown rice. This triggers Step 3, severe localized friction spikes. The hard silica acts like a grinding stone, and your pearlers effectively become highly efficient, profit-destroying grinders, pulverizing your precious head rice into worthless brokens.
Section 4. The moisture critical window. Thermodynamic tolerances. 16%. Let me be perfectly clear. This metric is a non-negotiable directive. All that mechanical precision we just talked about, entirely useless without strict moisture control. You have to hit a highly specific 16% moisture tempering window. You temper the grain via steam vapor injection to exactly 16% internal moisture before it ever touches a single abrasive element on the floor.
Because if you don't, you hit point of failure number 3, subcritical tempering. Allowing grain to enter the milling chamber below a 14% moisture threshold is amateur-hour operational incompetence. Rice exhibits extreme crack susceptibility when its internal moisture is too low. If you ignore this thermodynamic window, you guarantee mechanical catastrophe inside the chamber.
Here are the actual physics of that failure. Step 1. The grain is tempered below the 14% threshold, leaving the internal starch matrix inflexible and brittle. Step 2. It gets hit with the rapid mechanical shifts and shear forces of the milling chamber. Because it can't absorb the kinetic energy flexibly, we hit Step 3. Catastrophic internal fissure propagation. Microcracks rapidly spread through the starch endosperm, and the kernel literally shatters from the inside out. Your head rice recovery numbers absolutely tank.
Section 5. Friction mechanics. Exfoliation versus grinding.
Now moving into the purling chamber, you have competing mechanical principles for bran extraction. On one hand, you have carborundum-coated abrasive whitening. This relies on a rough, stone-like surface to aggressively grind away the pericarp. Fast, sure, but incredibly harsh. Alternatively, you have the much more precise induction of grain-to-grain friction. Here, the pressure of the grains rubbing against each other gently exfoliates the outer layers. This specific dynamic is engineered to preserve aleurone layer integrity while still extracting the bran.
But you can easily ruin that with point of failure number 4, weighted plate overbalancing. At the discharge end of the purler, there's a plate held by a weight that controls back pressure. If someone incompetently overweights this plate, usually chasing a wider degree of milling, they create severe internal back pressure. The grain is trapped, grinding intensely. The friction generates extreme heat, and instead of delicate exfoliation, the grain basically boils in its own moisture. Once again, thermal cracking and your broken spike.
Section 6. Value stabilization, maturation and parboiling biochemistry.
Let's look at the final traps. Points of failure 5 and 6. Lipase-induced acidification and defective ambient steeping. Remember that 8% full-fat bran stream? Well, if you fail to permanently inactivate the endogenous lipase via extrusion heating, the fat rapidly hydrolyzes. Within hours, your valuable, nutrient-dense byproduct is destroyed by Lipo-Oxygenase rancidity, turning into highly acidic, unmarketable waste. And if you're using defective ambient temperature steeping for parboiling, you're inviting anaerobic fermentation, massive off-flavors, and Maillard browning that horribly discolors your final product.
The ultimate defense here requires absolute biochemical control. Advanced modern paddy parboiling uses complex ancillary equipment and vacuum pressure dynamics to execute a hot water soak at exactly 60 degrees Celsius, just a tiny fraction below starch gelatinization. This exact temperature acts as a biochemical shield. It hardens the endosperm, making it wildly resistant to mechanical breakage, and it forces water-soluble B vitamins straight from the bran into the core of the grain. You lock in commercial value well before Maillard browning can even think about occurring.
So I'll leave you with this one highly cynical question to ask about your facility's unit operations. Are you actually precisely preserving the aleurone layer, balancing thermodynamics and defending your yield? Or are you just mechanically milling your profits right into rancid dust? When you look at the data, industrial milling is not farming. It is a highly sophisticated science. And frankly, it's probably time to reconsider every single technical tolerance on your floor.